Cubbage.
Hi, Mr. Nabowski.
Hi. So today we're going to be talking about what calculations we're going to have to use with waves and things you're going to need to know. Okay? So the first thing you need to know is wavelength. What do you think that might mean?
Well, a wave, I think, is something that goes like this.
Right.
And then the length, I guess, would be the length of how far before it dips up and comes back up.
So, okay, so here's my wave right here that I'm drawing. All right. So if I were to measure the length of it, I don't measure everything here. So the top of the wave is called a crest. So we measure from one crest to the next crest is my wavelength. So like that's where I would put a ruler if I could measure it with a ruler.
Oh, okay.
So that is the length of my wave.
So we don't measure the whole wave.
Don't measure the whole wave.
Or several of them, just from crest to crest?
From crest to crest.
Okay.
Or from trough to trough, which would be the bottom of it.
Oh, okay.
Okay. So we're going to have that wavelength in our equations. We're going to signify that with the lambda. So the lambda looks kind of like an upside down Y.
Upside down Y.
Okay, so whenever you see that upside down Y, think wavelength.
And is the length, you said like we can measure it with a ruler?
Right. So we're going to measure it in meters more often than anything, but any measurement of length could be a measurement like nanometers or centimeters like we've written here. Okay. But our formula is going to be measured in meters, so if I give you in centimeters, you're going to have to convert it to meters to get to the right place in the formula. Frequency is the next thing that we need to talk about. Frequency is going to be abbreviated by an F in your equations.
Oh, that's easy enough.
Okay, so that makes sense, right? So what do you think frequency means?
Well, frequency, like if I frequently go somewhere, I go there often. So maybe it's like how many times it happens?
Right. So if we're talking about waves, imagine, okay, well, here's your beach right here. So how frequently, how often that wave crashes into the beach is your frequency. Okay? So that is waves per second.
So if it's slow, it might just hit the beach every couple of seconds, but if there's a lot of waves, it might
very quickly
be faster.
So, and once again, we're only talking about the top of the wave, so the crest of the wave. And that's going to be measured in Hertz, Hz. And I'm going to spell that out, Hertz. That's an R there, I promise. All right. There we go. Can you read that? Okay.
I can.
All right.
Good.
Good. Hertz. Okay. The other thing you're going to need to know is energy. What is energy?
Energy is what we use to do things, right?
Right. So what does a wave use energy for?
To move.
Right. So the energy is like the movement energy of that wave, and we're going to measure that in joules, which is probably a new word for you. Joules. It was named after a scientist, like so many other things.
Okay.
Okay. Let's see.
So just like we use meters for distance, we use joules for energy.
Right.
Gotcha.
Right. It's just its unit. It's just a number, something we can attach to a number to say what it means.
Gotcha.
Okay. So we've got a couple of constants, a couple of numbers that are never going to change. One of them is called Planck's constant, and that is going to be, you're going to see that as an H in your formulas. So whenever you see an H in your formula, you can automatically sub it in with this number. That's not a minus in front of it. That's just a dash. So that is 6.63 times 10 to the negative 34 joules per second.
Seems like a very small number.
It's a very small number. It's actually the amount of energy like a little photon, a little packet of light has when it hits you. So if one little beam of light hits you, it's not going to transfer very much energy to you. It's very, very little. Okay, so, and the other thing is the speed of light, which is the speed limit of the universe, the fastest thing that we can think of, which is going to be represented by the letter C, and that is 3.0 times 10 to the 8 meters per second,
Wow.
which is actually really, really fast.
300 million meters a second.
Yep.
That's crazy fast.
Right.
You said that's the speed limit of the universe?
Yes, that's the fastest anything can go, according to physics as we understand it right now. So, we've got a couple of equations we're going to use. C, which is the speed of light, is equal to the wavelength of that wave times its frequency. Okay? And then we also have E, which is the energy of a wave, is equal to H, which is Planck's constant, times the frequency. Okay? So these are both very simple little equations, three variables, well actually only two variables because two of them are constant. So I'm not so good at algebra, so I like to put those into triangles. So that'll make it a little easier. So the two things that are next to each other always go on the bottom of the triangle. So my lambda goes on bottom here, my frequency goes on bottom here, and then the C is on top.
So everything's under the C.
Under the C.
Under the C.
Okay. And then our other formula is E equals HF. I'm going to draw its triangle over here so I have a little bit more space here. And E is by itself, so that's the one that goes on top. And then H, my Planck's constant, goes in this part of the triangle, and then my frequency goes in this part of the triangle. Okay? Easy enough?
I think so.
Okay. So, whenever I'm going to show you a couple of practice problems, and we're going to use the easy method, the triangle method first, and then we'll show you another method too. That might be easier for some people, but for most people this first method will usually work better. Okay, so it says, calculate the wavelength in meters of radio waves having a frequency of 2.5 times 10 to the 6 hertz. Okay, so now when you've got a problem in chemistry, what's the first thing you should try to do?
Identify our given.
Okay, so our given is 2.5 times 10 to the 6 hertz. And what did we say hertz was?
That was frequency, right?
Frequency. So that's going to be our F in our equations. Our frequency is equal to that.
And you said earlier that each one of these has a constant, so we're kind of given a free one, right?
Mm-hmm. Yeah.
What was the free one for wavelengths?
So, well, let's see. So because we're solving for wavelength, I'm going to go ahead and underline that. So I'm going to know my wavelength, which is that upside down y, what lambda, is equal to what I'm trying to figure out. So that's going to be a big question mark there. And then, so I've got frequency lambda, so I know that's actually supposed to be an H there. I know it kind of looks like a lambda, but that's my lambda and my frequency and speed of light. So it is that first equation, C equals lambda times the speed times frequency. So I can plug all those numbers into the triangle where they go. Okay, so I know C, my speed of light, is this number up here, the 3.0 times 10 to the 8th.
Speed limit of the universe.
Okay, and then I know my frequency, which was in this triangle here, is 2.5 times 10 to the 6th power. Okay, so then I just divide those two numbers. So, Mr. Cubbage, while you go get a calculator, I'm going to go ahead and set up the other strategy. And so our other way to solve this, we're going to have frequency. We're going to be solving for the same thing. So this first part is going to be exactly the same. But what we can do is we can rearrange our formula first. So we already knew we were going to use the C equals lambda times frequency, and I know I'm trying to solve for lambda, so to get the lambda by itself, I divide both sides by the frequency, and my frequency cancels out on this side, and I'm left with a nice clean equation of lambda is equal to the speed of light over frequency. So for both of ways we're doing this, we're still dividing the speed of light divided by the frequency, which is what we have set up in this triangle here, speed of light divided by the frequency. So to plug that into our calculator, what we do, we always open a parentheses whenever we're dealing with exponents like this, because our calculator will go a little wonky if we don't. So we open the parentheses and we do 3.00 second. EE is my times 10 to the power of 8, close my parentheses, divided by, open a new set of parentheses, and it is 2.5 second EE, and it is to the power of 6. Close my parentheses, and I hit equal, and I get 120, which is lambda, so it's our wavelength. So we know our wavelength will be in meters.
So how did we know it was in meters?
Because we knew we were solving for lambda, wavelength. And we knew wavelength is measured in meters. And that meters is the one that's in our formula.
Oh, that's from our formula, okay.
Okay?
So we'll always find it in meters.
Right.
Okay.
So, now, oh, there we go. We've got another practice problem here. So in this one, we have 4.2 times 10 to the 8.
I think that's a 3 there.
Or 10 to the 3.
Yeah.
Sec. So I'm assuming that's supposed to be hertz and not sec there.
Probably.
Okay.
Back
So
to the -1.
yeah, I think that's a typo, and that's supposed to be hertz here, because it's a frequency. So my F is equal to 4.2 times 10 to the third power.
They were probably trying to say 1 per -1 second or something like that. I was just wrong.
So then I'm calculating the energy. So how do we abbreviate energy?
Energy was one of those real easy ones. That one was just E, right?
Right, E. So energy is what we're solving for. Okay, so we're looking for our formula that has frequency and energy in it. Which one was that?
Oh, that was E equals HF.
E equals H times F. Okay, so I wrote that down here because we're going to use that second strategy to rearrange the formula here. But here we're going to use the triangle. So we know that the triangle was E on top, H and F here. So our frequency, which is what we put right here in this part of the triangle, is 4.2 times 10 to the third power. Okay.
Oh, was H a constant?
H was a constant. Okay. And H,
The Planck constant.
is Planck's constant, which is 6.63 times 10 to the -34. So that's
Very
what we.
small number.
That's what's going to go in this spot right here, which I said was 6.63 times 10 to the -34. Okay, so we're just going to end up multiplying these two numbers because they're next to each other here in this. So the other way to solve for this that we would get the same answer for is to rearrange this, but we don't have to rearrange it because energy is already by itself.
Looking for E?
So it's just H times F, which is what we're doing up here. So we will multiply those two numbers by each other. So what we do is we open a set of parentheses because we're dealing with exponents. 4.2 second E is my times 10 to the third power. Close my parentheses. Times, open a set of parentheses, 6.63
-34.
to the power of -34. Make sure you never hit that minus button for the -34 because the calculator doesn't like that.
Oh, yeah, that negative's on the very bottom, right?
Mhm.
Okay.
Okay, and we end up with, we'll round that to 2.8. times 10 to the power of negative 30.
And always make sure that you include that exponent right there,
Right.
or you'll be very, very wrong.
That's very important.
Yeah.
Okay.
All right. If you have any questions, ask a teacher.
All right.